Hey, good morning, everybody. This is Mr. Ainsworth. We're going to get in Chapter 3, Section 4, and we're going to be talking about concavity specifically here, and we're going to be also working with what's called the second derivative test and show you how to apply it. So, first what we want to do is define concavity graphically and also, specifically what it's all about. So let me first say that we're going to say that f is differentiable on an open interval. Okay? I'm going to define it first. So let's let our function f be differentiable, okay, on the open interval from a to b. Okay? So that there are no cusps, and so that the tangent line exists everywhere along that interval from a to b. Now let's draw a picture first before I define it here. So let's suppose we have a function that looks like this here, and we'll call that f. All right, now this is a picture of what's called concave up. Okay, right here, concave up. Okay, but why is it concave up, and how do you tell that without looking at the graph? Okay, and just by using the second derivative. Well, if you take a look at the tangent line at any point, let's suppose that we're taking a look at the tangent line here. Okay, there's f prime. F prime is in red. We're going to notice that as we cruise along from left to right, the tangent line goes from negative to 0 at the bottom there to positive, and it's obviously increasing from left to right. F prime is increasing. And remember, f prime is the slope of the tangent line, so f prime is the slope of the tangent line, and it's increasing from left to right. Slope of tangent, and in this case it's increasing. Oops, increasing there, okay? So from left to right, the slope of the tangent line is negative, and then it goes down to 0, and then positive, and it gets steeper and steeper and steeper as you move along the function here. We say that it's increasing. So when we define concavity, we simply say that f is concave up. F is concave up on AB, okay, on the open interval from A to B, if f prime is increasing on that interval. If f prime is increasing, okay, on that specific interval from A to B. Okay, now when I draw a picture of concave up, I draw it like this in general. Okay, concave up. Now, it may not be concave up on a particular interval. It may be concave down, in which case it looks like this. So if f there is looking like this, we say that it's concave down. Okay, that's what it looks like. Now, what's happening to the slope of the tangent line as we go from left to right along the function? Well, let's draw a picture of that too. All right, over here on the left side of the function there, notice that f prime is, some positive number. And as you move along the function here, it's steep, and then it's not so steep as you move from left to right. And at the very top there, it's 0, and then over here it becomes negative, and it's decreasing. So the slope of the tangent line starts off as a big positive number and then kind of mellows out to 0, and because of that it's decreasing. So here f prime is decreasing on that interval. Okay? The slope of the tangent line is actually decreasing. It starts off big positive number, it goes to 0 and then negative. We say it's decreasing. And because of that, when we define it, we say that f is concave down, okay, on the open interval from A to B, okay, if f prime is decreasing on the interval. DC for decreasing, going down, okay, as opposed to going up on that interval, on open interval from A to B. And when I draw a picture of concave down, I make it look like concave down here. So my concave down, my symbol looks like that, okay? That's specifically how to define concavity. Now, how do you test it without looking at the graph? How do you test to see if a function is concave down on a particular interval or concave up on a particular interval without looking at the graph? Just when you be given a function here. Well, we need a test for that. We're going to call that a concavity test. Okay, we're going to suppose that f prime and f double prime exist. That's first derivative and second derivative. First derivative, second derivative. Suppose they exist, okay, given some function f. Okay, if that's the case, then we say that if f double prime, which is just the second derivative there, is greater than 0, and I'm specifically saying there that it's positive. That's a fancy way of saying if the second derivative is positive now. All right, for all x, okay, on a particular interval, we'll call it interval I, or you can say, you know, from a to b, let's say. Now again, this little symbol in mathematics that you just saw, this upside down capital A, means for all. Okay? That's typical. So if f double prime, or the second derivative, is greater than 0, which means it's positive, on a particular interval from a to b, then we say that f is concave up on that interval. Because if it's positive, if the second derivative is positive, it's going to be concave up. Then f is concave up on that interval, whatever the interval in question is. Okay? And we'll call that interval I in general. Okay, so what we need to do is evaluate two derivatives, the first and second, and we're going to test the second derivative, and we're going to do a sign analysis on the second derivative, and if it's positive, okay, it's going to be concave up. If it turns out to be negative, then it's going to be concave down. So number 2, if the second derivative is less than 0, which implies that it's negative here, on I, all right, for all x on I, excuse me, all right, for all x on I, that means everywhere on the interval, okay, everywhere, then f is concave down, and f is concave down on that interval, okay, concave down. So if the second derivative is greater than 0, which means it's positive, you're concave up. If second derivative is negative, it's going to be concave down. All right, and it's called a second derivative test, or a concavity test, and we need to take two derivatives of the function to make that happen, and we do a simple sign analysis. Okay. Now we also have something called a point of inflection, or inflection point. I abbreviated that IP, inflection point. All right, and inflection points are points where the function changes concavity. Points, okay, where the function changes concavity. Changes concavity. There is one case where it may not, so we'll explore that as well. But an inflection point is where a function can change concavity. All right, so what I need to say first is that f has to be continuous on the open interval. Okay, so let's let f be continuous on an open interval from a to b. Okay, and let's see be an inflection point. Let's see let's see be an inflection point, IP, okay, inside the open interval from a to b. So it exists somewhere between a and b. Okay, if that's the case, then c comma f of c, all right, is an inflection point if f changes concavity from up to down or down to up. Okay, then c comma f of c is an inflection point. Is an inflection point of the function now. Okay, of the function of f if the function, which we're going to call f in general, changes concavity. Changes concavity from up to down to up. Okay, from either up to down, or down to up. Okay, and there are three possibilities where that happens. Okay, so let's go over the three possibilities and draw a simple sketch of each. And so you can see what I'm talking about here. The first graph here, let's take a look at this one here. Okay, and there's the function in blue here. We have an inflection point right about here at C, comma f of C. There's f of C right there, whatever that is. All right, because the function to the left of C is concave up, and to the right is concave down. All right, so C, comma f of C is an inflection point because it changes concavity from going concave up on the left to concave down on the right. Okay, it may not look like that, so let's go ahead and show you the other possibility here. Suppose we have something that looks like this. They see the may look like this here. Where we have a change in concavity right about here, where the slope of the tangent line is horizontal here. This is f prime. In this case, it's equal to 0. Here, f prime was not 0. F prime was, some positive value. But simply put, to the left of C here, it's concave down, and to the right of C, it's concave up. So we have a switch in concavity, or the function could be going the other direction, I suppose. All right, and we have the last case where you see inflection points is where you have a vertical tangent line. So let me draw a situation like that, where you might have something that looks like this here, where that's F here, okay? And the tangent line, or the point of inflection, excuse me, the IP, point of inflection here. This is your IP here. This is your IP here. The tangent line may be vertical at this point. F prime may be vertical. Okay? That happens sometimes. It happens on the cube root function. And you notice that in a previous lesson. Okay? So it goes from concave up to concave down. It could also be going from concave down to concave up. It really doesn't matter. The inflection point is where it changes concavity. Okay? If you have a change in concavity, then you have an inflection point. Okay, so how do you find these inflection points? Because we need to find them in order to graph functions that have inflection points. Okay, so let's talk about that. How do you find inflection points? Well, let's say this. If C, comma, f of C, okay, where, the inflection point, okay, the possible inflection point, if it is an inflection point, all right, then f double prime at C equals 0, or the second derivative evaluated at C does not exist. Okay, meaning that it's not differentiable at x equals C. So what we're going to have to do is we're going to have to evaluate the second derivative, set it equal to 0, and solve for that possible C value. And we're also going to have to look at where the second derivative is undefined or non-differentiable. And that happens in root functions, and that happens in rational functions. We look at the denominator and see where it's undefined. So in this section here, to test for concavity, we have to use the second derivative. To find the points of inflection, we have to find the second derivative. And we're going to set it equal to 0, and we're going to solve that equation. Okay? Now, a little note here is that the converse of this is not necessarily true. Converse of this is not always true. Is not always true. Okay? In that, meaning that if you have if you set the second derivative equal to 0 and you solve for all possible values of C, they're not always inflection points. what you're going to have to do is do a sign analysis on the second derivative and check for a change in concavity from either up to down or down to up, because sometimes it doesn't change concavity at all, in which case that C value is not an inflection point at all. Okay, so let's go for it here, and let's take a look at a function. And in this case, we want to determine the open intervals and where it's concave up or down, and we want to find the points of inflection right here, the inflection points. Okay, so the first thing we do is we take a few derivatives. All right, so let's go for it here. And the very first thing we have is that f prime is equal to negative 3x squared plus 10x. That's first derivative. To find the inflection points, though, we need the second derivative, and we're going to set the second derivative equal to 0. So I'm going to differentiate again. I get negative 6x plus 10. I'm going to set this equal to 0 to find the inflection points. Okay? Set it equal to 0 to find inflection points. Always the second derivative. Okay, we use it to test concavity, and we also to use it for inflection points, as you're going to see. So what we need to do is figure out where it's positive and negative. If the second derivative is positive, it's concave up on an interval. If its second derivative is negative, it's concave down on that interval. So we do what's called a second derivative sign analysis. Second derivative sign analysis. Okay? All right, so f double prime. Now, in order to figure out the possible inflection points, I've got to solve this equation, which I forgot to do at this point. So I need to subtract 10 here. I get negative 6x equals negative 10. Divide by 6, negative 6, excuse me, and I get x is equal to negative 10/6. Okay, or negative 5, or excuse me, positive 5/3. And that's 1 2/3. Okay, so that's my possible inflection point. And I say possible because it may not have a change in concavity there. We have to test it. You can't just assume it. So this is a possible inflection point. So what I'm going to do is place it on the graph, 1 2/3 here. And obviously it's between 1 and 2 somewhere, right about here, I guess. All right. And I want to pick values to the left and right of that to test concavity. I'm going to test concavity here. Okay, and when you test concavity, you evaluate your second derivative. Let me highlight that. I'm going to be using this function right here to test concavity. What's happening to the left of 1 2/3? What's happening to the right? Okay, so let's get started here. I'm going to take f double prime. I'm going to evaluate that at 1 because that's to the left. Just pick an easy value to the left. And evaluate the second derivative. And then you get negative 6 times 1 plus 10. That's 4. Okay, and that's obviously greater than 0. It's positive. So what I do to represent that is I put the symbol for concave up here, and I put a plus sign because when the second derivative is positive, you're concave up. Let's go back up to what I said earlier right here on the concavity test. I said if the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. Okay, that is our concavity test. Now I want to pick a number to the right of 1 2/3. I want to pick 2. So just pick easy values to work with, okay? Anything to the right of 1 2/3 will do. 2, 3, 4. Don't worry about fractions or anything. So you get negative 6 times 2. Add it to 10. That's negative 12 plus 10, or negative 2, and that's obviously negative. So I symbolize that with a negative sign, and that represents concave down. Okay? So remember, this is negative infinity over here. This is positive infinity here. All right, and so if I want to summarize where on what open intervals is it concave up or down, let's do that right here as a summary. All right, I can say the following here. I can say concave, okay, up on the open interval from negative infinity to 1. I can also say concave down on the open interval, excuse me, not 1. That should have said 1 2/3. Let me fix that. Going a little too fast here. 1 2/3. There we go. my possible inflection point right here is 1 2/3, not 1. I just use 1 to test it. And it's concave down to the right of 1 2/3, so I can say 1 2/3, comma, infinity. Those are called open intervals, which means they do not contain the endpoints. Okay? So, do we have an inflection point? That's the key. Do we have an inflection point right here? And the answer is yes in this case, because it changes from concave up to concave down. There's a change in concavity. Change in concavity there. Okay, right there. Okay, and that becomes an inflection point. Okay, so we have an inflection point at 1 2/3, comma, something. Okay, so what I need to do is evaluate the function at 5/3 and figure out that value. Okay, so let me just, I'm going to just work on the left side here, do my arithmetic here. F of 5/3 should be equal to negative 5/3 cubed plus 5 times 5/3 squared minus 7. And you need to, be good at the arithmetic so you can work this out. Okay, this becomes negative 125 divided by 27 plus, let me see, 25 times 5, 125 divided by 3 squared, 9, minus 7. Okay, and then I have to combine fractions here. So negative 125 27ths plus multiply both of these by 3. You get 375 divided by 27 minus 7. That gives you 250 divided by 27 minus 7. And the arithmetic, that becomes 2 7/27. And that goes here, 2 7/27. So this is your inflection point. And if you actually graph this function on the TID4 and plotted this point 1 2/3, comma, 2 7/27, you'll see that you have an inflection point there because there's a change on concavity. In fact, you know what? Let's just pause the video for a second. I'll show you. Okay, I pulled up another program which is a little bit better than your TID4 to illustrate what I'm talking about here. You notice we have our same function right here that I plotted on this graphing software, and notice that our inflection point was 1 2/3, which is about 1.6. Notice my point right here is about 1.6 as well. Not exactly 1 2/3, but it's very close. And this is an inflection point right here because the function changes from concave up in this region here to the left of that, to the left of 1 2/3, to concave down. And that's exactly what we're talking about when we discuss inflection points. It changes concavity. And cubic functions do that all the time. Okay? And that's what we're talking about here when we discuss concavity and inflection points. Just want to show you. All right, let's go on and continue. Let's try with a different function so you have a little bit more experience. Okay. Okay, let's continue here. We want to figure out where it's concave up and down, given the function x plus 2 cosine x. We need to first take a derivative, all right, f prime, and we get 1 plus, well, it's going to be minus in just a minute. The derivative of cosine is negative sine, so really, let me fix that. 1 minus, all right, 2 sine x. Now I need a second derivative to find the possible inflection point, so let's differentiate again, and you get negative 2 cosine x here. And the derivative of sine is just cosine. Derivative of 1 is 0. We're going to set this equal to 0 to find possible inflection points, all right, which means that after dividing by 2, we're going to have to solve when cosine x equals 0. Okay, and when is cosine x equal to 0? Where it's equal to 0 at the top of the unit circle at pi halves and at 3 pi halves. So x equals 0 at pi halves and 3 pi halves. And it keeps on going on. There's an infinite number of solutions here. So I'll tell you what, let's limit the problem here. Let's find the inflection points on the closed interval from 0 to 2 pi. Okay, because if we don't, there's going to be an infinite number of them. So let me add that into the directions here so that we limit our number of inflection points and limit our number of intervals where it's concave up and down, because this function oscillates infinitely. So we have possible inflection points there. We're going to need to test them and test the second derivative. And when we test the second derivative, we focus in on this function here. All right, so let's do a second derivative sign analysis here. Let's plot pi halves here, plot 3 pi halves here, and let's pick angles in between these values. So we have 3 intervals to test on, and this is a negative infinity here, positive infinity here. Okay, let's test our first interval from negative infinity to pi halves. I'm going to pick something in between there, like pi fourths. Check that out. So f double prime of pi fourths, that's less than pi halves, and that's going to be equal to negative 2 times cosine of pi fourths. Well, that's negative 2 times root 2 over 2, which is a negative number. It's less than 0. So I don't care what it is. I just care whether it's positive or negative, because that tells me where it's concave up or down. And because it's negative here, that's negative. It's negative there. It's concave down on that interval. Okay, what's happening between pi halves and 3 pi halves? Well, let's check that out. Let's pick an angle in between there like pi. All right, and that's negative 2 times cosine of pi, which is equal to negative 2 times negative 1, which is positive. Now, if it's positive, that means it's concave up. Looks like that. Concave up. Let's pick a number to the right of 3 pi halves. Like, how about 7 pi fourths? How about that? So f double prime of 7 pi fourths, that'd be negative 2 times cosine of 7 pi fourths. Okay, now cosine of 7 pi fourths is a quadrant 4 angle, and cosine's positive there. This is a positive number. Times negative 2, well, that's negative. So it's less than 0. It's negative. And because of that, I know that it's concave down on that interval from 3 pi halves to positive infinity. Okay, and in this problem, we're just trying to find the open intervals where it's concave up or down. Okay, so let's do a little summary here on that. And then let's also find the inflection points. We're going to have to find the inflection points too. Okay, so let's do a little summary here. Put in blue here. Okay, it's concave down on 2 intervals. Okay, on negative infinity to pi halves, and from 3 pi halves to positive infinity. It's concave up on only 1 interval from pi halves to 3 pi halves. Question is, do you have inflection points at pi halves and 3 pi halves? And the answer is yes in both cases, because there's a change in concavity from down to up and then from up to down. So this becomes an inflection point. So does this one. Okay, and we have 2, but where are they? So what are the inflection points? Well, let's figure that out too. Okay, we have pi halves comma something and 3 pi halves comma something. Okay, and then wherever you want a y value, you just simply substitute these points into the function. So let's go up a little bit so we can see that function. We're going to take these and substitute them into the original function and evaluate it first at pi halves. And so we get pi halves plus 2 times cosine of pi halves. Okay, and this becomes 0 here. 2 times 0 is 0, giving you pi halves. Okay, so this is a pi halves comma pi halves. And then f of 3 pi halves would be 3 pi halves plus 2 times cosine of 3 pi halves. Okay, and again, that's 0 there. So you get 3 pi halves here. Okay? Okay, now if that was too fast for you, then no problem. Just go ahead and rewind the video. Pause me, rewind a little bit, and listen to it again, okay? But I'm applying the same strategy to all of these problems. To test concavity, you need a second derivative. And then using the second derivative, you do a sign analysis, in between the possible inflection points and see where it's negative or positive. If it's negative, it's concave down, positive, concave up. And then to determine if you have an inflection point, you determine if you have a change in concavity from down to up or from up to down. Doesn't really matter. But you have to have a change in concavity in order to have an inflection point. All right, so the last thing what we need to do is discuss what's called the second derivative test and then apply it. Okay, so we're going to let f be a function such that the first derivative is equal to 0, which means that c is a critical point. That's what that means. C is a critical point. That's how we find critical points, is by setting the first derivative equal to 0. And, oops, I said it right here. C is a critical point. And let the second derivative exist on AB containing C. Okay, now if C is a critical point, that's important. And you evaluate the second derivative at C, that critical point, then the following must happen. Case 1, if, okay, the second derivative, f double prime, at C, that original critical point you found using the first derivative now, okay, if it's greater than 0, which means it's positive there, that's a fancy way mathematically to say it's positive, then f has a relative min, okay, at C comma f of C. Okay, why is this a min? Well, let's discuss that for a moment. If the second derivative is positive at that point, at the critical point, then it must be concave up. And if it's concave up, it's got to look like a valley. And at valleys, when you consider valleys here, they have relative minimums. That's the reasoning behind it. Now that may not happen if the second derivative evaluated at your critical point is less than 0, which means it's negative here, okay, or concave down, concave down, then that becomes like a hill, and hills don't have minimums, they have maximums, they have relative maximums. So if the second derivative evaluated at your critical point is less than 0 or negative, then your function f here has a relative max, okay, at C comma f of C. Okay, then just think about it. If it's concave down, because the second derivative is negative, it's got to have a relative max as opposed to a relative min. Now, if the second derivative, third case, if the second derivative evaluated at a critical point is equal to 0, okay, then the test fails. Okay, which means it doesn't tell you anything. It fails. And what you have to do is you have to use the first derivative test instead. Okay, use the first derivative test instead. Okay, so let's go for it. Let's show you how to use the second derivative test. It becomes useful sometimes. And it's just another way to see if you have relative extrema versus looking at the first derivative. You can use the second derivative if you're given it, or if you want to find it. Okay, so let's take a derivative here. We want to find the relative extrema. And remember, that's just, what's the relative min and max? That's what I'm saying. Using the second derivative, okay? Using the second derivative test. Not the first derivative test, but the second, which means we need to evaluate two derivatives. So first derivative is negative 15 x to the fourth plus 15 x squared. Second derivative is equal to negative 60 x cubed plus 30 x. Okay? Now, those are my first and second derivatives. This one gives us critical points. Okay? So actually, let me erase that arrow. I need to set it equal to 0. I need to find the critical points of the function. So I'm going to set it equal to 0 to find critical points. That's C. All right, and I'm going to do that over here. I'm going to factor out the 15x squared. So 15x squared gives me negative x squared plus 1 equals 0. All right, obviously x equals 0 there. And then at this point right here, when is negative x squared plus 1 equal to 0? Well, let's just work on that. Let's say, subtract 1, divide by negative 1. Holy cow, x is plus or minus 1. So I have critical points at 0 and plus or minus 1. Let me highlight those. Those are critical points. And what I want to do is test the second derivative at those critical points to see if I have a min or max. So instead of doing a first derivative sign analysis and see where it's increasing or decreasing to find the relative extrema, I'm going to use the second derivative. Okay, so here we go. Second derivative test right here. Second derivative test. So I'm going to evaluate the second derivative at 0. That's my first critical point. And I'm going to get negative 60 times 0 cubed plus 30 times 0, and it's a whopping 0. So test fails there. I'm going to have to resort to the first derivative test. Bummer. Okay, I'll do that in a minute. Second derivative evaluated at 1. Okay, so negative 60 times 1 cubed plus 30 times 1. Okay, that's negative 60 plus 30. That's less than 0. Okay, it's concave down at that point, which means we have a relative max. Okay, so we have a relative max there. Notice I know that even without using the first derivative test. Okay, at 1 comma f of 1. Now f of 1 you just put right here, 1 there. So it's negative 3 plus 5 or 2. Okay, so we have relative max at 1 comma 2. Now I want to check the second derivative at negative 1 as well. So I get negative 60 times negative 1 cubed plus 30 times negative 1. That's 60 plus minus 30, that's positive. Okay, that means it's concave up. If it's concave up, it's got to be a valley, and you must have a relative min. Okay, at negative 1 comma whatever f of negative 1 is. So I need to put a negative 1 in here. So f of negative 1 is equal to negative 3 times negative 1 plus 5 times negative 1. That's 3 plus 3 minus 5, that's negative 2. So I get a negative 2 there. So I have a relative max at 1 comma 2 and a relative min at negative 1 comma 2. There's some end results there. And I need to still test 0 because the test failed. Okay, the second derivative test failed at 0. So I need to resort to the first derivative test. So let me do that, and then I'm done. So on the first derivative test, I need to test f prime at 0 and see where it's positive or negative, or see where it's increasing and decreasing. So here's negative 1 and here's positive 1. I need to test like 1/2. Okay, everybody, eyes up here. This is my my first derivative is right here in blue. I can either use the original f prime or the factored f prime. Okay, but eyes on the blue. So I need to test f prime at let's say negative 1/2. Okay, I'm going to use this one here. If I take negative 1/2 here and I square it, I get something positive. So I get 15 times something positive that's positive times, and then I get negative 1/4 plus 1. That's still positive, so times positive there. Not positive 1, just positive. And well, that's a positive number, which means it's increasing here. Okay, it's increasing. And then to the right of 0, how about positive 1/2? Okay. Well, again, I get 15 times something squared, that's positive. And then I get negative 1/4 plus 1, that's still positive. So I get positive here. Okay, well, it turns out to be neither a relative min or max, because it's on both intervals it's increasing, so there's no change from up to down or down to up, or from decreasing to increasing, or vice versa. So this becomes neither or not a min or max, not min or max. Okay. Okay, so we only have a relative min and a relative max. It turns out at 0, I think we have an inflection point. You can test the second derivative and see that. Okay. So we were asked to find the relative extrema. I did that. We have relative max at 1 comma 2, relative min at negative 1 comma negative 2, and I'm done. Okay. So give your homework a shot. Check the answers in the back of the book and come prepared for questions on Monday, and I'll see you then.